Good evening, my dear friends and my dear students. So today we will be talking about the catalysis continuation. This is my third class on catalysis. So all of you know that the slogan says by Bernard Shaw, science never gives the solution, it gives 10 more questions. I think you wondered, what is this? That means the science always gives the concept for application to develop. That's why once you solve a concept, the another new concept will be developed. Thereby another 10 questions will be developed on that. So every time the science makes you to learn more and more and be confident. So now keeping this slogan, so I would like to continue the class. So in the last CPP class, so I made given 10 questions for you people. So in that I observed, so one of the problem was misunderstood by the students. So that's the reason I would like to solve this question. The question I think you can see on your screen, which is already displayed. The question goes like this: the failure of the Freundlich adsorption, based on that the question was given to you people. The question goes like this. Now I think you can see on your screen the Langmuir adsorption at high pressure, what will happen? So this is the question I have given to you people. So when you look at this question, the question goes with the options like this. So at high pressure, so we will all of you know that the pressure increases, but when we talk about your Langmuir adsorption, so he says x by m, which is equal to theta, or which we can say so k theta. So this theta, which will later be represented as, that is x by m is equal to AP over 1 plus BP, that is the partial pressure at the mass as well as the area which is given by the adsorbent. Now the pressure, if it becomes more than 1, that is greater than 1, so thereby this becomes the equal to, that is x by m, which is exactly equal to AP over BP. Thereby the pressure, if you remove, the option which I given, x by m is equal to A by B. Very simple. As the pressure increases, you know that the molecules gets with each other, where it overcomes the van der Waals force of attraction, thereby the pressure increases, thereby so the x by m, which is exactly equal to A by B, which is the answer which I given as option A. I think now you understood how actually we have to solve this problem. So now in this today's class, I will be talking about the catalysis. In the last class, we had discussed basically about different types of adsorption isotherms, Langmuir adsorption isotherm, we discussed the characteristics, we discussed about the failures of Langmuir adsorption, Freundlich adsorption, and I gave some important information about BET isotherm, that is called as a BET, usually call it as, so Baumer, Emmett and Teller isotopes. So that is the adsorption isotherms, where we discussed about how actually the mechanism of adsorption which occurs on the surface of any solid can be explained. So now in the today's class, I will be talking with respect to the continuation of your adsorption, where it finds a lot of application. That is where we would like to talk about the catalysis, which is one of the eminent and the important application of this adsorption. So now I would like to take you to the virtual board, so where we will be talking about the adsorption and the catalysis, the continuation part. Now we will be talking about today's topic of discussion goes with respect to introduction of catalysis. So I will be talking about, so then we will be talking about the types of catalysis, then we will be talking about the characteristics, so then activity and selectivity of the catalyst. So this is the first part I will be talking about. In the second part, we will be discussing about how actually the promoters, the catalysis will be affected, or how the rate of reaction will be controlled by using the catalyst. So that is where we will be talking about in today's class. So all of you know that whenever we talk about any new topic, So, there should be an introduction to be given to that, because one should understand what actually and how this branch of science of catalysis has been established. So, I think you know that. So, in 1863, before the identification or definition of an atom, the Berzelius JJ was identified certain chemical substances which we use, which will increase the rate of a reaction without themselves being consumed. So, this is the concept which was developed and he was taught, and later that as he called as the process called as catalysis, and that chemical substance he called as the catalyst. He believed that the function of such substances was to loosen the bond which holds the atom together. So, how actually this process has been established? So, this is very simple. When we take a cup of water, so where I am going to add a solute. The moment if add a solute to a solvent, automatically there the solute plus solvent interaction takes place. So, thereby the solute get dissolution into the solvent, then you get a solution of that particular compound. So, how actually this happens? So, this is by breaking the bonds. So, now what actually without using a catalyst is happened here, or without using any chemical substance is happened, but certain reactions which requires a catalyst. That is what, suppose if you take the best example I can give is, take hydrogen gas plus oxygen gas at room temperature. What do you expect? Nothing will happen. But instead of that, if I take hydrogen plus oxygen in presence of a platinum catalyst, so then I can expect the H2O. So, that means this chemical substance plays a very important role. So, that is why, so I will be talking about how actually this catalyst works. So, now the term catalysis was coined by the Berzelius. What he says, according to the Greek word kata means whole, that means it involves itself wholly, and it basically loosens the bonds which are held by the atoms or the elements or the molecules to form that particular compound. So, now what it does, so earlier bonds which were there with the reactants were broken with the help of these substances, and they make the component to get into a new substance. So, that is why we will be talking about this catalyst. So, this catalyst, as the name itself says, it is the chemical substance which alters the rate of a chemical reaction, itself remaining chemically unchanged at the end of the reaction. That means, so you may find what is this complicated statement, itself chemically unchanged at the end of the reaction. So, that means it helps the reaction to occur, but physically or so chemically the composition of that chemicals which we are using as a catalyst will remain after the reaction or the process completion. So, this process of converting a reactant or to give a product in presence of a substance, that is what we call as the catalyst, is called as catalysis. The catalysis is the process in which a reactant gets converted into a product with the help of a chemical substance called as catalyst, is called as catalysis. Now, the question comes, the catalyst always increases the rate of reaction? No, always not necessary. It depends on the type of reaction which you are doing. If the reaction is happening by itself spontaneously, we can reduce the reaction rate also. So, that means we may increase the rate of the reaction, or we may also decrease the rate of the reaction by adding these chemical substances. A catalyst also enhances the rate of the reaction, called as the positive catalyst. That means, so this is simply called as the process positive catalysis, or simply called as catalysis. Certain substances which I said which retard the rate of the reaction are called as the negative catalyst, or the process is called as negative catalysis, and this should be specified always when you are talking about negative catalysis, because the positive catalysis is generally termed as the catalysis, whereas the negative term negative catalyst will be always said as negative catalysis, because it leads to confusion if you say just catalysis. The question comes next is, what is the positive catalysis and negative catalysis? So, now with respect to this two types of catalysis. So, we are going to have the basic type of classification of catalysis. The basic two types of catalyst exist, but the third type is also very important, which we cannot neglect, because as a human, so we will be knowing this, because all our food material which we take as a food, once it goes to the stomach, it will get for catabolism. So, that means the word catabolism also takes, without the help of the enzymes, the bioenzymes, this process cannot happen. That is the reason. So, in chemically we talk about two types of catalysis, that is called as homogeneous catalysis, and the second one we called as the heterogeneous catalysis. The third type catalysis which I said, that is called as enzyme catalysis. This is basically taken much interest with respect to the biological systems. So, now what actually the homogeneous catalysis talks about, and what exactly the heterogeneous catalysis talks about, what is the basic difference between these two. So, this is what we will be talking about in the another few sessions. So, and the third type is, so this I will be talking about in the next session, because this involves the lot of concepts should be understood how actually the catalysis occurs, because the catalysis itself is a new terminology. So, where we are going to use a small chemical substance which brings about lot changes in the process. So, coming to the first type of the catalysis, that is called as chemical catalysis, which we called as the homogeneous catalysis. As you all of you know that the homogeneous catalysis, the homogeneous is a one word, and the catalysis already we had discussed. The homogeneous, when we call the substance as homogeneous, it should be physically same. That same in the sense, physically same means, what am I talking about? Single phase. When we talk about single phase, what is this? I am not talking about phase, FACE, I am talking about single PHACE, that is very important. Okay, people will have two phases. This is a single phase compound. So, when we talk about a single phase, you all of you understand, so which is not easy to separate. That is what, if I take a water, H2O in 1 cup of water, so I add another cup of water to this. So, I think you get a homogeneous solution. If I add a water to another water molecule, that is a cup of water, you get water which is homogeneous. So, now can you separate this water? Very difficult, because they are homogeneous, that is what we call as a single phase. Now, if I give one more example, so I take iron powder, I will add sulphur powder to this. So, I get FeS. There also you can see this is also solid phase, this is also solid phase, and I get the final solution which is the resulting compound which is also solid phase, which is also single phase. Can I call this homogeneous? No, because if I drop a magnet to this, immediately the iron will get attracted to the magnet and sulphur gets separated and iron gets separated. Thereby, we cannot call this as a homogeneous. So, that means you do not just look for the phase, you have to look for the another one is the composition as well as the mechanical separability. That means, without spending energy, if you are able to separate, then that is comes under the category of heterogeneous. If it is not possible to separate easily without spending energy, then that system we call it as homogeneous. I think you understood what I said. So, homogeneous means it should be a single phase, along with it is mechanically not easy to separate. So, such compositions are called as homogeneous. Hence, we will be talking about such process with respect to catalysis. So, that is what in homogeneous catalysis what basically occurs is the catalyst which you are taking as well as the reactant which you are talking about should be in the same phase. I am not bothered about the product what is going to happen, but please bear it in the mind, the reactant which you are going to use and the catalyst which you are going to use should be in the same phase. Since such process is called as homogeneous catalysis. Your product may be in solid phase or liquid phase or gaseous phase. If it is in the gaseous phase, it is very difficult to separate the product. That is one of the major failure of this homogeneous catalysis. So, now when we talk about the examples for homogeneous, I think you are well aware of these reactions, that is sulfur dioxide conversion to sulfur trioxide with the help of a catalyst called as nitric oxide. So, nitric oxide means you may be laughing, correct? No, this is a laughing gas also. When we inhale this gas, the people will start continuously laughing. So, that is one of the special property of this nitric oxide. So, this nitric oxide makes this reaction faster to get SO3, Then you may be wondering what is the use of this SO3. So, by making use of this SO3, when I add a calculated amount of water to this and in presence of vanadium pentoxide as a catalyst, you get the king of acid called as the sulfuric acid. So, this is a beautiful process from sulfur trioxide to conversion to sulfuric acid, which involves a process of catalysis. So, now you can see over here the SO2 combines with oxygen in presence of nitric oxide, you get SO3 along with the byproduct, that means the catalyst will be left free without its in chemical oxidation or reduction process. That means what NO I have used, it is then given out. That is one of the property of the catalyst. So, that I will be talking about what are the characteristics of catalyst in the next future minutes. So, the next is when I talk about inorganic reaction, people will be fond of organic chemistry also, because some of you like organic chemistry very much. That is what I am taking the formaldehyde, that is acetaldehyde or formaldehyde you can take. So, then when we take the iodine vapors, then you are going to convert that into methane plus carbon monoxide gas. So, here, so basically it undergoes for reduction. So, thereby you are able to get the addition of hydrogen occurs to this molecule, and here you can see very clearly your reactant as well as your catalyst are in the same phase. Hence, this type of catalysis is called as the homogeneous catalysis. So, next which I talked about the gaseous phases. Some people are very much interested in the solution phases also. So, now when we look at the solution phase reactions, so here this is one of the best example which you come across. So, that means whenever in summer when you go to a sugarcane juice shop, okay, they will give this sugarcane, that is what C12H22O11, that is nothing but cane sugar juice. When you add water to that, and here I am using the catalyst which is also in the liquid phase. Now, your reactant which I am taking as in the liquid phase as well as your sulfuric acid, that is nothing but acid catalyst. Not only acid, this sulfuric acid you have to add, so you can add lemon or citric acid. Okay. So, that is also makes this process to occur, but the process of catalysis will be slower when compared to sulfuric acid. Why I am telling sulfuric acid cannot be added, because we cannot drink this juice if you add sulfuric acid. But for chemical reactions, if you want to find out the rate of the reaction, so to make this reaction faster, we add sulfuric acid, so that this sucrose which is called as a disaccharide broken down into monosaccharides. One is the glucose unit and another is the fructose unit. That is why C6H12O6 along with the sulfuric acid and the dot water molecules will come out with this. So, now you have to be very careful here in the liquid state also. When I am talking about the reactant, if it is in the liquid phase, your catalyst also should be in the liquid phase, then only that is called as homogeneous catalysis in the solution phase. So, coming to another example, I think this ester, I think everybody finds happy with this, because whenever we cut an apple, you find a fruity odor. So, that is what when in the laboratory also you can make this ester smell very simple. Add an alcohol, organic acid with respect to an organic alcohol, you get a beautiful smelling compound called as the ester. So, in this case I will be taking an example of ethyl acetate when it undergo hydrolysis in presence of once again the sulfuric acid. So, it gives us the two products, one is the acetic acid and ethanol. Okay. Now, so here also you can look at the ethyl acetate is in the liquid phase, and your sulfuric acid, the catalyst which I am using for this process is also in the liquid phase. So, thereby, so this is called as the homogeneous catalysis in solution catalysis or solution phase. Similarly, when we talk about another example, so this is the hydrogen peroxide and decomposition. If I am doing, I think decomposition means all of you know that it loses its character and it gets into a new product. That is what we talk about. So, here in this case you can look over here, iodine ion I am taking, it is not a iodine molecule of gas, that is what is very important. So, that means we are taking iodide ion, thereby, so that means we are passing this iodine into water and you are getting the iodide ion. So, that is mixed with the hydrogen peroxide. So, then so we are going to get the water molecule along with oxygen. So, here also when you look at, so you have hydrogen peroxide which is in the liquid phase as well as your iodide ion which I have taken in the solution phase. So, then this type of reaction is also considered to be the homogeneous catalysis in solution phase. So, now coming to the heterogeneous catalysis. So, when we talk about heterogeneous catalysis, it goes like this: the reactant as well as your catalyst will be in the different phases. So, that means the most of the time your reactions which occurs, so will be in the gaseous phase and the catalyst will be in the solid phase. So, that means here you can think of the clear adsorption phenomena comes over here, whereas in the earlier two cases you can see the miscibility or the solubility things comes into picture, whereas in the case of heterogeneity or heterogeneous catalysis we directly take into the help of the adsorption process there, because so I am going to use the reactant may be in the gaseous phase or in the liquid form or in the solution form, but your catalyst will be always in the solid form. So, hence this type of catalysis which we term called generally as the contact catalysis, because so there should be only a physical contact or a chemical contact comes into picture, whereas in the earlier cases there is a complete solubility interaction between the reactant as well as your catalyst takes place, whereas here the catalyst will be only providing a role of adsorbent and your adsorbate will be the gaseous molecule or maybe your the liquid solution form which you are using as the reactant. The contact catalyst, in which the catalyst will be taken as the finely divided form as well as in the form of gas. So, which depends upon the type of reaction which you are looking. So, this form of catalyst will find lot application in industry. So, now when we talk about this heterogeneous catalysis, why it finds lot of application in industry? The question goes like this: why it may be finding lot of industrial importance? The basic reason for this is the product when we get it, it is in the different form when compared to your catalyst, thereby very easy to separate. Hence, so we will be talking with respect to the heterogeneous catalysis more, because we are going to invest less amount of energy to separate the product and the catalyst, whereas in the earlier cases of homogeneous catalysis, when you look at the product as well as the catalyst in the same form, so then it is becomes the cross contamination which we call it as, or separation becomes huge a task. That is the reason all industries looks for the heterogeneous catalysis. So, before getting into some of the examples for this heterogeneous catalysis, so this is the time for you to announce the contest time winner of yesterday's class. So, I congratulate Mr. Ganesh, who won one atom session to his account by answering the right answer for the yesterday's contest question. The today's contest question will be on your screen right now. So, I always say, so just think for the right answer in the right time and make your answers faster. And all the best who are taking the contest time right now, and do the best. I hope you are done with your contest time question. So, now we will continue with the today's session the heterogeneous catalysis, okay, examples. Now, here once again the gaseous phase as well as the liquid phase will be taken into account. So, when we talk about the gaseous phase experiment, I take the same example which we had discussed as in the earlier case of conversion of sulfur dioxide to sulfur trioxide. So, what is the process over here is, so SO2 when combines with your oxygen, okay, it gives us the product as SO3. Here you can see the gaseous phase is there, here oxygen is in the gaseous phase and here this also in the gaseous phase. Now, I will use a catalyst here which is the platinum, or I can use vanadium pentoxide V2O5. So, now when you look at the end, whenever this product conversion takes place, so your platinum will be in the solid phase, and whereas your this sulfur trioxide in the gaseous phase. Now, without doing any extra energy or spending extra energy for the separation, the gaseous product just separates out because of its higher kinetic energy. They will be collected in the top, whereas the platinum particles will be collected in the bottom because of their solid nature. So, this is very easy process, that is why heterogeneous catalysis finds much applications. When you coming to another example which I will be talking about, you are well aware with the Haber's process of manufacturing of ammonia. So, there also we will be using nitrogen as one of the reactant and your hydrogen gas is another reactant, where I will be talking with respect to gaseous state of reactions, and we will be using a catalyst which is nothing but iron in presence of molybdenum or aluminum oxide as the promoters, which I will be talking about what is those role later. So, now look for this iron as a catalyst, so which will convert into 2 ammonia molecule. So, now you get the product as gaseous and the iron will be left free without any chemical change in the composition. So, thereby, so these type of catalysis finds lot of applications. So, if I look for this, the next molecule if I am talking about is organic chemistry, where we will be talking about ethylene. So, which is CH2 double bond CH2, which is in the liquid state or in the gaseous form we can make it. So, when I add hydrogen to this in presence of nickel as a catalyst, so once again, so you can find the nickel is in the solid state and you are going to get a molecule of CH3 with CH3. So, that means ethylene is converted into ethane by the addition of hydrogen molecule to this. So, this is all with respect to the gaseous reactions. If I go for the same reactions with respect to aqueous solution or in the liquid form, so the catalysis goes like this. So, that is what I can give the same example, the hydrogen peroxide when it is made to interact with the platinum material or the platinum gas. So, this will get converted into 2H2O plus O2. So, once again you get your platinum as such in the process. So, or if I go for a look for a reaction like this, the benzene C6H6 which is a liquid, then it is made to react with the CH3COCl which is called as ethynyl chloride. Ethynyl chloride is one of the important component in the polymer industry to get majority of your araldate kind of molecules, that is adhesives which we call it as. So, when it made to react with a catalyst called as aluminum trichloride which is anhydrous form. So, this will give a product of C6H5COCH3 along with the product HCl comes out and you get AlCl3 as the catalyst which is. So, this AlCl3 or FeCl3 is finds a very much important role in all your Friedel-Crafts reactions of organic chemistry. So, that is called as acetylation reaction when we do in all these cases. So, where we are going to introduce CH3CO where this AlCl3 plays an important role. So, that is why, so this heterogeneous catalysis in the liquid phase finds lot applications. So, coming to heterogeneous catalysis with the solid component. So, this few reactions are available because you all of you know that the solid reactions are not much importance because they do not react easily because they are held together with a solid bonding, thereby it is very difficult to find much reactions. But still if I want to give the example which we can give is the decomposition of KClO3, that is potassium chlorate which is catalyzed by MnO2, manganese dioxide. So, this is the reaction where we are able to get the compound called as the molecular oxygen along with the KCl, that is potassium chloride, and your manganese dioxide comes out. Now, look at here This is in the solid state, whereas this is in the gaseous form. So that is why if you want to generate dimolecular oxygen, so then this is the one of the reaction which we use as the heterogeneous catalysis in solid phase, because here also reactant is also in the solid phase, as well as your what we call as catalyst, which I am using manganese dioxide, which is also in the form of solid. So next, so which another one example which we want to give for solid catalyst which you are thinking of is the alloy formation, Au plus copper. Okay, they themselves have active centers to form AuCu. This is what happens in the gold formation. There I do not require any of this, just it is required, automatically you get an alloy. So I cannot call this as a solid reaction, because the lattice points of gold and silver copper will get into each other with the help of temperature. So here temperature is very important in this case. So next, once we understood what is the heterogeneous catalysis and what is homogeneous catalysis, so we will be talking about some kind of reactions or some kind of properties, what this catalyst will actually do, and what is this role of this catalyst, and how actually it behaves in these chemical reactions to bring about these product conversions. So that is what, if you want to understand a human very well or your friend very well, so you should understand his characters. So like that, if you want to understand this chemical substance as a catalyst, so then I should have the certain characteristics for this. That is what the first characteristic of any of these catalysts or these chemical substances, which I call it as a catalyst, should possess this is. That means a catalyst remains unchanged in its mass and in chemical composition at the end of the reaction. Just if you recall back what all the examples which I given in a gaseous form, in the solution form, or in the solid form of the reactions with the help of this catalyst. So this always goes, the final product which we get, the mass and the chemical composition is always same, it is not going to change. Next, the second characteristic of this catalytic reaction or this catalyst is the small quantity of catalyst is generally needed, we do not require. It is nothing but like this, when you are taking a curd rice, when you are making your curd rice at home, so you are not going to add the salt in terms of grams, you are going to add in terms of milligrams. So like that, the entire salt will get into your curd rice and it will give you a taste. Similarly, when we talk about this catalyst is also used in very small quantities. So that is why the small quantity in the powder form or in the finely divided form, which makes these reactions to an huge extent. So that is what, how actually it happens, that we will discuss by in the next sessions, how actually energy of activation and molecularity of the reaction are affected by the use of catalyst. The next important third point is the catalyst will be more effective in the finely divided form. That is what you have to remember, because if I take the whole catalyst in the form of a solid or a block, if you measure the length and breadth, you get area. But if I make this into fine powder, you can see the number of particles, each will have the multiple areas, thereby you get large surface area and the gaseous molecules can penetrate between the spaces and they can bring about the chemical change by getting absorbed physically or chemically. Whereas if I take the solid block, so you can find only on the surface of this will get in, but the inner part of this material does not allow the penetration of these gaseous molecules or the liquids as a reactant which you are taking. Hence, the yield or the rate of the reaction will be decreased if I use the block of a solid catalyst. Hence, we have to use in the powder form, that makes the larger surface area or active centers which we call it as. So next is the catalyst is specific in its action, it cannot do multiple actions, it is done for a specific compound. So if I want to get this product, I should pre-think which catalyst should be used for this. Suppose the hydrogenation of oil, that means in your house the oil, if you get open in the kitchen after 2 days, especially in the winter season, so this will get hydrolysis, that means it gets the absorption of moisture, thereby it gets the process called as rancidity, the oil will develop a bad smell. In order to avoid this, what chemically we do is, we take the triglycerides or any oil, so we add nickel to that in presence of hydrogen, so thereby we convert that into vanaspati or dalda, thereby the rancidity of oil can be reduced. So that is why, so this, if I want to do this vanaspati or conversion into dalda, I cannot use any other catalyst except nickel. So that means they are very specific in action. A catalyst, even in the case of Weber's process of manufacturing ammonia, I cannot use something else, I have to use iron only for the process. A catalyst in general cannot initiate a reaction. This is very important. At any point of time, this catalyst does not initiate. That is what I gave one example. If you remember, the water plus hydrogen plus oxygen in the formation of water, if you do this, take these two gases at room temperature, if you keep for years together, you never get water. But if I bring a platinum to this and if I give energy to this, automatically this will get initiated. Some of the examples like this. So that means it cannot initiate, but some of the reactions which requires some kind of initiation from these catalysts. The next important role is a catalyst does not affect the final position of equilibrium, although it shortens the time required to establish the equilibrium. This is very important. So by using a catalyst, I cannot make the equilibrium to shift. It is like this, from your house to your college, the distance is always fixed. How you move to your college from your house, it matters. If you go by walk, it takes maybe 10 minutes. If you go by bike, it may take 5 minutes. So this is different with respect to the vehicle. That means your transportation mode. Similarly, the catalyst here acts as a transporter for the reactant to come to the surface of the adsorption process and then converts into product. So thereby, so whenever I talk about equilibrium thing, you all of you know that in the case of initially the concentration will be 100% of the reactants. As the time progresses, so they get decreases. As the time this product formation also increases. So that means the point where this forward reaction as well as the backward reaction meets, this is called as chemical equilibrium. Now, so by adding a catalyst, the time taken for reaching the equilibrium will be fastened or delayed. So that depends upon whether you are doing positive catalysis or negative catalysis. If I add a catalyst, so the equilibrium distance will be reached faster, thereby it does not affect the yield formation. The quantity of yield is not going to get affected by this process. It is only rate or velocity of the reaction is increased, but not on the yield. So just by shifting the equilibrium, that means making the equilibrium to reach earlier, so the product can be obtained continuously in larger quantities. So that is what the point number 5 which I have talked about. It does not affect the equilibrium, or there is no shift in the equilibrium, only the equilibrium will be reached faster or it is slower. Next, the change in the temperature alters the rate of the reaction, because you all of you studied in chemical kinetics and thermochemistry, as the temperature increases by 10 degrees, that makes the reaction to get double. So that makes here the kinetic energy once is given to the molecule, so that makes the reaction faster. Okay, so this is all about the characteristics of catalyst. So now we will be talking about next point of this characteristics when we talk about how actually this reaction of catalysis brings about. So when we talk about a catalyst, it's specific. How it is specific? Suppose if I take a nickel, so assume nickel atoms are like this. So where I am taking nickel over here, nickel over here. In the case of hydrogenation of oil, so the hydrogen comes over here, attaches to this, and adsorption takes place, hydrogen to this. So this helps in bringing out the next molecule of your oil to the surface, and this hydrogen is donated to the unsaturated sites of your alkene, thereby that gets saturated. So if I use a molybdenum in between, so thereby what will happen, this is your nickel, so then if I use another mixture of catalyst, so molybdenum over here and nickel over here, so and once again the molybdenum over here. So now this makes a lot of differences. So hydrogen comes over here and you have a gap over here. So thereby the new molecule can come and enter here, thereby it decides the specificity of the reaction by making a physical adsorption or chemical adsorption process. Now if I take any of this molecule as a catalyst, so you all of you know that the surface is unsaturated, that is what we said in the earlier classes. So when I take this catalyst, the surface is highly unsaturated and it is having valence sites. So this is called as the active centers. Once these active centers are unbalanced, thereby they expect the molecules to come onto the surface, and thereby they undergo for physical adsorption process or maybe chemical adsorption process. During the process of this adsorption, the product formation takes place, which makes the unwanted product to be left on the surface. Suppose if I am doing a petrochemical reaction, or if you think of your what we call as catalytic converters which are used in your vehicles. So, they contain rhodium as one of the catalyst, which converts the nitro NO compound to combines with oxygen to give NO2 and CO plus O2 to CO2, because we know that carbon monoxide is very dangerous when compared to carbon dioxide. So, that is the reason we cannot live into atmosphere. That is why we give oxygen to that and convert into carbon dioxide, which is less toxic, but carbon dioxide is also dangerous. So, now this process will be done. So, in the process the carbon, if it gets attacks onto these active centers, the incoming gas may not be converted into carbon dioxide. That is called as the poisoning of the catalyst. If the active centers are covered by unwanted products and which reduce the effectiveness of the catalyst, so those substances are called as the poisoners, and the catalytic poison will be always discussed with respect which destroys the active centers on the surface of the catalyst are called as the poisons or catalytic poisoning. So, in the case of sulfur dioxide, that is conversion of sulfur dioxide to sulfur trioxide. So, there also SO2 plus O2. So, when we use a platinum, if it is gets converted to SO3, so here the product is the platinum is completely get poisoned by the presence of arsenic As2O3, arsenic trioxide. So, now when we talk about arsenic, where it is there? So, during the conversion of this sulfur dioxide to oxygen, so this arsenic is one of the byproduct, so which makes this poisoning of the clay. If the yield or the quantity or the quality of the SO3 reduces, automatically the sulfuric acid which you expect, which also loses the strength. So, next when we talk about how actually this another kind of substances which makes this, because I cannot stop the process of catalysis continuously, which is happening in the reaction. So, in order to make this process to happen continuously, so we add another set of chemicals which are not the catalyst, but they increase the efficiency of the catalyst. Those are called as the promoters. Promoters are the special type of chemical substances which are added to the reaction mixture to avoid the poisoning of the catalyst. So, which makes the process faster and faster, so without avoiding this. So, in the case of Haber's process of manufacturing of ammonia, so N2 plus H2, that is gives you 2NH3, okay, where we are using the iron as the catalyst and molybdenum as the promoter. So, now this molybdenum will take care of the poisoning of the iron effectively. That means, iron will be kept active for majority of the time, so that this molybdenum oxide will get the unwanted compound onto its surface and keeps this iron in the more active state. Thereby, the process of conversion of nitrogen to ammonia with the help of hydrogen in presence of molybdenum will give a good yield. So, this is where the promoters plays a very important role. Next, another type of catalysis which we talk about is the auto-catalysis. When we talk about auto-catalysis, the name itself indicates the catalysis or the product, one of the product of the reaction itself acts as a catalyst for that reaction to happen. So, such kind of catalysis is called as auto-catalysis. The auto-catalysis is a process in which the product which is going to be formed itself acts as the catalyst. Hence, that reactions are called as auto-catalysis. If I give an example for auto-catalysis, it is like this. So, that is what I will be giving an ester example once again, CH3 C double bond O, O C2H5, ethyl methyl ester. This is. So, when I add water to this, so this will give us an acid Ca3COOH plus C2H5OH. So, here the acid which is going to be formed as acetic acid as one of the byproduct which helps this process to occur continuously. So, thereby this kind of reactions are called as auto-catalysis reaction. Or if you look at the colloidal solutions which we will be talking in the later classes, there, so arsenic hydride AsH3 which gives rise to As plus 3H2. So, now this hydrogen which is going to be formed here, so which makes this reaction to happen. So, thereby this becomes the example for auto-catalysis. So, now, so we are discussed in this today's class about what is catalysis, what are the different types of catalysis like homogeneous catalysis, heterogeneous catalysis, and the characteristics of catalysis, and we discussed about the different conditions in which the reaction occurs. So, if you want to know whether you understood my topic clearly or understood the concepts today what I taught, so this is the right time for all of you people, just go for class practice session. So, after I have selected around 10 important questions from the concepts which I taught you today. So, I request all of you to just immediately go for your CPP class practice session. So, right now all the best my dear students.